The basic layout is what is STFT, why it is required when we have DFT. Then we will introduce spectrogram, look into computation and interpretation of spectrogram, how to improvise the spectrogram, windowing and changing the n value. Then we'll look into the application and at last the conclusion. Short time Fourier transform (STFT) is a Fourier-related transform used to determine the sinusoidal frequency and the phase content of local selections of a signal as it changes over time. DFT tells us how many frequency components are there in the signal, but it doesn't tell us where do those frequency components occur. Hence, DFT is not suited for non-stationary signals. To understand this, let us take a chirp signal. When we draw the DFT of this signal, we get something like this. We give a 180-degree phase shift to this signal and the DFT is the same here. But we know that these two signals sounds totally opposite. To understand the idea behind spectrogram and how it is constructed, let us take a time domain music signal Xn, which sounds something like this. Now, if we multiply this signal with a window Wn minus L, which is located at time t dash, which is the center point of these two extremes, the length of the window is capital N. We get the resultant signal as a part of an original signal, which can be mathematically represented as Xn into Wn minus L. Now, if we take the FFT of this signal and draw the power spectrum of it, we get this graph. Here, the frequency is along the x-axis and the power in decibels is along the y-axis. Further, we rotate the graph 90 degrees so that we get the frequency along the y-axis. From here, we get our spectrogram strip. Here, the time is along the x-axis, frequency is along the y-axis, and the power is along the z-axis, or you can say the color axis. This strip is located at time t dash. The coloring is done using the help of this scale. This can be understood by an example. Suppose at this point the power is say minus 35 decibels. So minus 35 decibels means it will be here. So in this graph we will have a yellow color at this location. Going further, let us now take a chirp signal. Here windowing will give me a spectrogram strip. We slide the window along the positive x direction to get another strip. We continue the process to get the complete spectrogram. SDFT of the signal Xn in frequency domain is complex value. It is difficult to handle, so we plot the power spectrum, that is SDFT mod square. Due to the large range of frequency, we choose 20 log of SDFT. Such a visualization of spectra gives us the spectrum in decibels. Such a two-dimensional log spectra visualized with heat map is called as spectrogram. So, previously, we have created and read a spectrogram. Now, we will try to analyze a spectrogram. Here, there is a speech signal whose corresponding spectrogram is given below. There is a sound of E at 0.5 seconds and sound of A at 1.3 seconds. In the spectrogram also, we can see that there are comb-like structures at these corresponding times. Here, the first horizontal line is the fundamental frequencies and the above horizontal lines are the overtones above the fundamental frequencies. We have the vertical lines in the spectrogram at 0.8 second and at 1 second. These lines corresponds to the abrupt sounds. In these are generally the stop constants like the letter D, T, K, approximate, and area which have lot of energy in high frequencies are the noise signals. Here there is a area at 0.3 seconds and at 0.11 seconds. Previously we have learned the concept of spectrogram. Now we will see the changes we can make to get a more clear spectrogram. For this we will be subjecting our chip signal to different types of windows of different lengths. Before going further, let us first understand what is the MATLAB function spectrogram. Here, x represents the signal, Rect win 256 is the window type and the length of the window. 250 is the number of overlap between the two consecutive windows. 256 is the length of the FFT, and Fs shows the sampling frequency, and y-axis shows the frequencies along the y-axis. First we will subject the chip signal to the rectangular window. This is the plot of spectrogram we get. The MATLAB code is this. It is fairly clear that the signals starts at around 100 Hz and it ends at around 4 kHz. But there are lot of artifacts in the side lobes of the around the main signals. Here this shows that there is lot of spectral leakage when we use a rectangular window. To reduce the spectral leakage, we can subject the signal to a Hamming window. This is the spectrogram we get after using the Hamming window, and this is the MATLAB code we get. Here we can see that the spectral leakage is less comparative to the rectangular window, but the frequency resolution also increased. To reduce the side lobe even lower, we can use the Blackman window. This is the spectrogram we get after using the Blackman window, and this is the MATLAB code. Here we can see that the side lobes are extremely small and the main signal really sticks out.
The case of the telephone keypad tones is an important example which we can take in order to understand spectrogram in a better way. For any application, a spectrogram should be precise enough along both time axis and frequency axis. We denote the precision along frequency axis as frequency resolution. The most important factor which determines this precision is the size of the time window which we have taken. If you take a very narrow time window, then we have very few data points, which means we don't have a lot of frequencies. Hence, the precision along time axis will be high, but the frequency resolution will be less. On the other hand, if you take a wide time window, we have more frequencies to consider, hence the frequency resolution will increase, but the precision along time axis will be less because we are considering longer periods of time. Another important parameter which we need to consider is the overlap between successive time windows. The more the overlap, the smoother is the time frequency plot, but we will have longer computation time. Each button on a telephone keypad generates a unique sound when pressed. The sound comprises of two frequencies. The combination of these two frequencies is unique for each button. It can be observed that 3 buttons are being pressed in this above audio clip. We will analyze the audio signal and find out the order in which these buttons are pressed. We will use MATLAB to find out the spectrogram of this audio signal. As explained in the previous slide, each button is a unique combination of two frequencies. Using MATLAB, we will plot the power density versus frequency for the signal. In the graph, it can be seen that there are 3 peaks. Here, 770 Hz and 1209 Hz correspond to the button 4, 770 and 1336 Hz correspond to the button 5, and 770 and 1477 Hz correspond to the button 6. What we don't know is the order in which these buttons are pressed. Now, we will give the audio signal and its sampling frequency as the input in MATLAB to find the spectrogram. Using short-term Fourier transform, the spectrogram will give us the power levels of the signal as a function of frequency and time. By default, Hamming window is used as the time window. Using different window segment lengths, we will try to improve the frequency resolution of the signal. We will use 480, 2000, 4000 and 8000 samples as a window length in order to find out the spectrogram. This is a spectrogram for window size of 480 samples. Different colors in the spectrogram indicate different power levels. These yellow colored regions have higher power levels when compared to the other colors. These blue blocks indicate the time between successive key presses. For this particular window size, we can see that the time resolution is good, however, the frequency resolution is not great. This is a spectrogram for window size of 2000 samples. Since we have increased the time window, we can see that the frequency resolution got better, but the time resolution is worse. Now for window size of 4000 samples, we can see that the time resolution is worse, but the frequency resolution got better. The same pattern can be observed for window size of 8000 samples also. The frequency resolution gets better with higher window size, but the time resolution is worse. At some point, we will obtain a good trade-off between frequency resolution and time resolution. That particular window size is selected for the spectrogram, and that spectrogram is considered for our analysis. For our example, the window size of 4000 samples is considered enough. This gives us enough frequency resolution as well as time resolution in order to find out the digits that we have pressed. So from this graph, we can see that 770 Hz and 1209 Hz occur first. Then occur 770 Hz and 1477 Hz. Later, it's 770 Hz and 1336 Hz. So this is the order in which these appear. From the above spectrogram, it is understood that the number corresponding to 770 Hz and 1209 Hz is entered first, that is 4. The number corresponding to 770 and 1477 Hz is entered second, that is 6. And the number corresponding to 770 Hz and 1336 Hz is entered last. Hence the sequence of numbers is 4, 6 and then 5. Here are some of the applications of spectrogram. In the early days, analog spectrogram was used to study bird sounds and animal sounds. Nowadays, digital spectrogram is used to study frequency modulation in animal sounds. It is also used for speech training deaf people. Spectrogram is used in phonetics and speech analysis, wherein we focus on how different speech sounds are produced and also sorting of speech sounds into different categories. It is used to check the performance of signal processors such as filters by analyzing the results of passing a test signal through it using spectrogram. Developing neural networks that are capable of speech recognition. Such speech recognition systems are used in voice assistants like Google Assistant, Alexa, Siri, etc.